We are taught to think in objects. A player has a position, a velocity, and a name. In our code, this looks clean. But to a CPU, this mental model is a performance disaster. Modern hardware doesn't see objects, it sees memory addresses. When we wrap data in objects, we aren't just organizing logic, we're organizing how that data sits in physical silicon. Today, we're exploring data-oriented design and why the way you've been taught to structure data is likely the biggest bottleneck in your application. We need to move from thinking about what things are to how the data is transformed. To understand why objects are slow, we have to look at the memory hierarchy. Your CPU is incredibly fast, but RAM is relatively slow. To bridge this gap, we have caches, L1, L2, and L3. When the CPU needs a piece of data, it doesn't just grab one byte. It grabs a 64-byte chunk called a cache line. If the data you need next is in that same 64-byte chunk, that's a cache hit. If it is not, the CPU stalls for hundreds of cycles waiting for RAM. This is a cache miss. In modern computing, performance isn't about how many instructions you execute. It's about how effectively you use these cache lines. In object-oriented programming, we often use an array of structures, or AOS. Imagine an array of enemy objects. Each object contains a position, a transform, health, and a name string. If we want to update the positions of all enemies, the CPU loads an enemy object into the cache, but that cache line is now filled with health and names, data we don't need for a position update. Worse, if these objects are allocated on the heap, they might be scattered across memory. The CPU has to chase pointers from one random address to another. This is the pointer chasing problem, and it's a silent killer of performance. Data-oriented design flips this. Instead of an array of structures, we use a structure of arrays, or SOA. Instead of 100 enemy objects, we have one position array, one health array, and one name array. Now, when we want to update positions, we iterate through the position array. Every byte loaded into the cache line is a position. There is zero wasted space. The CPU can see exactly what's coming next. This allows the hardware prefetcher to pull data into the cache before we even ask for it. By aligning our data with how the hardware actually works, we can often see speedups of 10 to 100 times. This shift requires us to stop thinking about what an object is and start thinking about what the data does. In data-oriented design, we group data by its access pattern. If two pieces of data are used together, they live together. If they aren't, they are separated. This is why entity component systems, or ECS, have become the standard for high-performance game engines like Unity and Unreal. They treat entities as mere IDs and components as contiguous arrays of data. This keeps the CPU fed, the pipelines full, and the frame rates high. It's a move from abstraction-first to hardware-first thinking. Let's look at the numbers. In a standard OOP loop, a single cache miss can cost 100 nanoseconds. In that same time, a modern CPU could have performed hundreds of floating point operations. If your data is scattered, your CPU spends 90% of its time doing nothing but waiting for memory. By switching to a data-oriented layout, you eliminate the waiting. You transform a memory-bound problem into a compute-bound one. Even in high-level languages like C# or Java, being mindful of memory layout can yield massive benefits. It is not just for C++ wizards anymore. Data-oriented design isn't a replacement for all abstraction, but it's a necessary tool for the performance-critical parts of your system. When you hit a wall, don't look for a faster algorithm, look for a better data layout. Remember, the CPU doesn't care about your class hierarchy, it cares about cache hits. Stop chasing pointers and start streaming data. If you found this technical deep dive useful, consider subscribing for more architectural insights. I'll see you in the next one.